Hello everyone. Welcome to this course on combinatorics. Our first lecture will be on one of the simplest techniques which is very often used in combinatorics. This is the method of pigeonhole or the pigeonhole principle. Now it may be the simplest in terms of the principle, the statement, and easy to understand. But that doesn't mean that it is by far the simplest to use. In fact, we will see several examples where you need to come up with some ingenious ways of thinking, so that we can we can put the question into the correct framework where we can apply the pigeonhole principle. Okay, so what is this principle? This is something that all of us know by heart. By experience, and we might have already used it many times. So this says the following: suppose you have, let us say, uh, you know, let's say k plus one pigeons. A flock of pigeons comes, and then there are k plus one of them for some k, integer, positive integer k. And then these guys sit into, let's say, k pigeonholes or k cages. Now, if k plus 1 pigeons sit into k cages, then we can say that at least one of the cages must contain two or more pigeons inside, right? This is something one can easily see, because if every cage had at most one pigeon, there are k cages, so there is at most k into 1, which is at most k pigeons inside, right? So therefore, we have a proof for the same thing, right? So we can say it in terms of balls and bins, that you have k plus 1 balls and k boxes for bins. So here are the k bins, let's say, right? And into this k bins, suppose we are going to deposit k balls, right? Now, what I want to prove is that at least one of them must have two or more balls. So if I want to avoid that, then I will try to put only, right, one in, at most one in each. But now I don't have a choice. I have to select one more here. If I have 6 balls, and I need to put at least two in one of them, right? So therefore, this is easy to see, and this is precisely what the pigeonhole principle is. Okay, so the proof was that if each box has less than or equal to one ball inside, then at most k into something less than or equal to 1, right? At most k into 1 equal to k balls can be there. So that is the proof, right? Now, this supposedly and very simple looking principle, how do we use it? Can such simple statements have some real applications in mathematics? In fact, we are going to see many very nice applications of this in today's lecture. Yes, we start with a very simple example. Suppose you have 8 integers, and you are asked to show that out of these 8 integers that are given to you, there are 2 among them whose difference is divisible by 7. Okay, no matter which integers, right, are given to you, you have to show that two among them are such that their difference is a multiple of 7. Now, how do you prove something like this, right? So now, if you want to use pigeonhole principle, the two things I need to figure out are what are the pigeons and what are the pigeonholes, right? Once you know what are the pigeons and what are the pigeonholes, we can very easily apply the principle, right? Because you know that there is some pigeonhole with this many, and then use it to solve whatever we want. But the question is that what are the boxes and balls, right? So how will you come up with answer to this, right? What are the boxes and what are the balls? And that is where the difficulty is. Okay, in applying Pigeonhole principle, always the difficulty is to figure out what are the boxes and what are the balls. Now, in this case, how will you proceed to solve this? Yeah, so let me state something very general in the start of this course. That combinatorics is a topic where you need lots of practice. You need to do several exercises to be able to solve questions. When you are asked for exams, for example, or like in later times, because unlike every other area in mathematics, there is less of a structural or general approach, but rather more of uh, more of a situation where you get some idea to click and then you can use it. You can use that idea to basically convert it into an already solved form or something like that. But or apply some general principle that you already know. But to be able to convert into that form where you can apply this, you need to come up with some way, and this usually is very very different for each of the problems depending on the flavor, and that is what makes combinatorics one of the most difficult topics to work with. Now, the only solution to this is to solve as many questions as you can. So when we finish the lecture, we will have some questions for you. That definitely you should try to solve. But apart from that, you also look at the book. The books that we suggest have many exercises, and go through the exercises and try to solve as many as you can. This might be a little bit time consuming, but there is no other way. Okay, so yeah, so this is my advice. Now, another advice I want to say is that whenever a problem is presented to you for a mathematics course, in fact, in any course, this is something that you should do. But in general, here, in particular here, I want to say that once you hear the problem clearly, before the solution is discussed, you please pause and try to think about this. Okay? This is something this is an advantage of an online course where you can basically pause the video and then you can try to solve it on your own, because on the class you have very limited time. The teacher can give maybe a few minutes to think, but if he gives a lot of time for you to think, then of course he cannot finish the topics, right? So therefore he is much more restricted there. But on the other hand, for a lecture like this where you have the option to stop the video and think about it, you should try to spend some time thinking, and then once you Once you think about it, you may not be able to solve it, that is okay. Once you think, several ways, and then you see the solution, that will definitely help you in understanding the applications tremendously. Okay, so with that, let us continue. So how do we go about solving this question, right? So first thing that you observe here is that you need to show that something is a multiple of 7, right? So basically what you are talking about is divisibility, right? So divisibility by 7. Now when you talk about divisibility, what comes to mind is that if something is divisible, then the remainder is 0, right? So then you get an idea that okay, we have to show the remainder is 0. No, we want to show that remainder is 0 for, right, what? The difference of two numbers. So when is the difference of two numbers have remainder 0? Well, if they have the same remainder when divided by the number, then the difference will have, that remainder will be gone, and then the difference will be multiple of the number that we are talking about, right? The difference will be 0 for the remainder. So remainder will be 0, and then we get a multiple. And that is what we are going to use here. Okay. So we are given 8 integers, and we have to show that difference is a multiple of 7 for some pair of them. So what we are going to do is that we take our integers and divide all of them by 7, one by one. So I take the first number, let's say a1, then a2, a3, etc., a8, right? Each of them I divide by 7. Then I get the remainders r1, r2, r3, etc., r8. Now, when you divide a number by 7, what are the possible remainders? Right? The remainder can be either 0, can be 1, 2, 3, 4, 5, or 6. Right? These are the only possible remainders when you divide by 7. Now, we have 8 numbers which you got as the remainders, and each of the remainder now can be put into one of the boxes labeled 0 to 6. Right? Because they are the remainders when divided by 7, so therefore it will be one of these numbers. So I'm going to put these 8 numbers into these boxes. So like an r1 goes here, r2 goes here, something like that, right? Now if I'm going to put it like this, then what do we know? Since there are 8 numbers, there will be some box in which 2 numbers will come, right? 2 of the remainders will be there. So that means that they must be the same, because I'm going to put a remainder into a box only if it is that number, particular number, 5. If it is 5, it is 5, right? The remainder is 5. So you take the corresponding numbers, let us say ai and aj, for which the remainder is the same. So ai minus aj has remainder 0 when divided by 7. That is why it is divisible by 7, right? Is a multiple of 7. So that's all there is, right? So once you figure out what are the pigeons and what are pigeonholes, that is it. There is nothing else. Yes, this is the first example. Now let us look at another example. Okay. So here the following question is given, that you are given a set with 11 elements. Now out of this set, you are going to make 4 element subsets. Okay? So you take any 4 of them, you get a subset. You take any some other 4, then you take another subset. So you pick 4 element subsets and take any 10 of them, whatever you like, right? So pick any 4 any 10 of the 4 element subsets of the 11 element set. Then 2 of these 10 sets that we are talking about must share at least 2 elements. Okay. So how do you show this? Okay, again, if you like, please pause the video and think about it. Now, okay, so here is the solution. So we are talking about two of these elements are going to have 2 or more elements in common. So if I want to show there are 2 elements in common, I can say that these subsets have, if you look at the 2 element subsets, they have an intersection. That is also good enough, right? If I show that these 2 sets have a non-empty intersection, right? And the subsets, 2 element subsets have non-empty intersection. That is also fine. So to do this, what I take is that I take each of the 10 4 element subsets, each of the 10 4 sets, and find and write down or consider the 2 element subsets of. Okay. Now, if you take a 4 element sets, how many 2 element subsets you can find? Okay, this is a question that you need to figure out. We will see the general method later, but most probably you are already familiar with it. One can easily show that there will be 6 of them. Okay, 6 of them are there, right? This is 6 each. So each 4 element set has 6 2 element subsets. Now there are 10 sets, so there are how many possible subsets? There are 60. So this gives 60 possible 2 element subsets. Now if any 2 of them are the same, that means that those 2 sets had intersection of size at least 2, right? So we want to show that this is the case, right? There will be 2 with this property, 2 will be the same. Now how do you show this? Well, we started with an 11 element subset, right? S is an 11 element set. Now you look at all possible 2 element subsets of this. So S has 55 2 element subsets. Now why? That is something that you need to figure out. Okay. Whenever I write why, that is the part that I have not given you proof, that you have to prove it yourself. You have to think about it and do it. Okay. So 55 2 element subsets are there. Now once you know that there are only 55 possible 2 element subsets, we can make pigeonholes, right? We make the 55 labeled boxes now with each of these 2 element subsets. Now we know that out of the 60 guys, each of them must be one of these 2. I mean, one of these 55, because there is no other possibility. They all come from the set S, right? All the elements come from the set S. So I'm going to put the 60 guys into the 55 boxes. So 60 is more than 55. So therefore, one box must have at least 2 inside. And that says that these two element subsets are the same. And therefore, uh, they must have come from 2 of these 2 different 4 element subsets that we are looking at out of the 10. So that is it. So we have proof that this is indeed the case. Okay, so here is the proof I have written here. Consider the two element subsets of each of the four element set. We show that some of the two sets must be the same. And for this, we look at the two element subsets of S as the pigeonholes. There are 55 of them. Again, think about it. Why? And each four element subset has 6 two element subsets. And again, why? And therefore, 10 into 6, which is 60 in total. By pigeonhole principle, 2 must be the same. And that's the proof. Okay. Now, the same pigeonhole principle we can write in a slightly more usable form, which I will say as follows. Suppose we have, instead of k plus 1 balls, let's say n into k plus 1. Now these are put into k boxes. So we have n into k plus 1 balls. We are going to put it into k different boxes. Then one of the boxes must have greater than or equal to n plus 1 balls inside. The same argument that we did earlier works, right? So here instead of 1 into k plus 1, and then instead of 1 plus 1, 2, we have n plus 1. Okay, because we know that if each box had at most n, then we have n into k, that is at most nk balls inside, right? So that is the proof. Now we want to use it to prove a very, very, very simple but very, very important result. Look at this example, right? It may look like nothing, but it is the start of a very big area in combinatorics, one of the most famous areas in combinatorics called Ramsey theory. And all this can be started from this particular question that we are discussing. But let us look at what is it for the time being. Okay, so any group of 6 or more people contains either 3 mutual acquaintances or 3 mutual strangers. So any group of 6 or more people. Okay, so you go to a bus stop, let's say, and you find 5 people sitting there, and with you there are 6 of them, or maybe there are 6 of them or 7 of them already. You join. There are many of them, many of you, and now the claim is that there will be at least 3 guys who have met each other, or at least 3 guys who have never met each other. Okay, so acquaintance means that like kind of friend, but if I meet you, but not really a friend or anything, then it's an acquaintance. But in short we will call it by friends. So there are 3 mutual friends or 3 mutual strangers, and we want to prove this using Pigeonhole principle. So how do you do this? Okay. Now, of course, we can use set theory to do this, but let us introduce a new concept just for proving this. Okay, this is a concept of graphs. What is a graph? A graph is a set. So you have a base set called a set of vertices, which we are going to denote as points or dots on the plane now, right? So here we have these dots, which are called the vertices of the graph. And then you have two element subsets, right? This forms a relation, a binary relation among the elements of V. Okay, so among the vertices, you have a relation which is called the edge relation. So whenever two vertices are in a relation, then I will say there is an edge, and I represent the edge by a line segment joining the corresponding vertices. And this is for the time being, this is a graph for us. Okay, so we have vertices and two element subsets, and now the advantage is that now this graph can represent many things. Okay, you can it can vertices can represent people, or it can represent terminals in a communication network, or or components in an electronic circuit, or many things like this. And then in the edges can be like, for example, the channels of communication, or you can say that like whenever I am, we are friends, then I put a line between them. There's a relation. Now we can even go further. We can say that I can represent different relations, like knowing and not knowing can be a relation. Now for knowing relation, I will put let's say blue edge, and not knowing relation, I put a red edge, like something like that. So now I can have colored edges, right? So if two guys know each other, then I put a red edge, or whatever, a blue edge between them, and if they don't know each other, I will put a red edge between them. So these are called edge coloring. It's called edge coloring. So you have a graph and then color the edges, and the color can represent properties, right, or relations. Now there are many types of graphs. We will not go into details at this time. We might look more of this in later part of the course. But for the time being, if every possible two element subsets are present for a vertex set, then this is called a complete graph. Okay, so here is a complete graph on three vertices. There are three possible edges there. All edges are present, so it's a complete graph. So with this in mind, we are going to design or model our problem in terms of graph question. What was our question? Any group of 6 or more people contains either 3 mutual friends or 3 mutual strangers. Now, if you show that suppose there is 100 people maybe, right? But if you show that out of this 100, if you take any 6, even within that 6 you have 3 friends or 3 strangers, then the entire group also have 3 friends or 3 strangers, right? So we don't really need to look at the larger numbers. We can just work with 6. So that is one advantage, right? So we are going to represent now a graph with 6 vertices, where each vertex represents a person, and you have all possible edges, and the edges are going to represent if two guys are going to be friend or not. Okay, so if there is a blue edge, then I say those two guys are friends. If A and B are friends, then there is a edge connecting A and B with blue color. Okay, so I take the 6 different people. Okay, now if I suppose I pick up a particular person, right, this guy, I can talk about him being friend with the other people, right? For example, like let's say uh, these two guys. These two guys are friends, let us say, right? Either they are friends or they are not friends. So we assume that one of them is the case. So let us say that they are friends. Now I take this guy and this guy. Maybe they are not friends. Then they are going to be strangers, right? So I'm going to put a red edge between them. Similarly, we can talk about this particular first guy being friends with the remaining 3 guys also, right? Now, by our pigeonhole principle, the second version that we looked at, if n into k plus 1 balls are put into k boxes, some box must have greater than or equal to n plus 1 balls inside. Okay. Now, here we have 5 possible edges, right, going out of this guy. So if I select this guy, there is one edge, 2 edge, 3 edge, 4 edge, and 5 edges. 5 edges are going out. Now, out of these 5 possible edges, we are going to color all of them with 2 different colors, right? Just 2 colors, either blue or red. If they are friends, blue edge. They are not friends, red edge. Now, applying the earlier principle that we talked about, we know that since there are only two boxes and we are going to put 5 inside, at least one of them must contain 3 or more inside, right? So which means that for some 3 the color is the same, right? At least, right? So maybe they are the friendship or not, whatever, doesn't matter. Both are identical, right? In symmetric cases, they are either friends or not friends, right? So the 3 of them must be of the same color. Let's say that 3 of them are non-friends. I mean, the friends, okay? And then 2 are maybe all of them are friends. That's okay, but we just want at least 3. So now we know that at least 3 have the same, right? These 3 give the same relation with this. Now, what do we know? So we have applied Pigeonhole principle. Okay, let us see, right? Now the question is that what can you say about these two guys, this person and this person? If they are friends, then I already have first. Okay, let us put some names just to be easy. So this is A, this is B, and this is C, and this is D, right? Now B, C, and D are all friends with A, right? Now B and C are friends. Then what does it say? It says that there is a blue triangle which says that all the 3 are mutual friends, which is what we wanted to prove, right, to begin with. So if there is a blue edge, then I am already done. So therefore I can assume that that is a red edge. Now similarly, if C and D there is a blue edge, then also I am done because I get a blue triangle. So this must be red. Now between B and D, if it is blue, again I get a blue triangle, so it must be red. But then I get a red triangle between B, C and D. So if I don't have a blue triangle, I have a red triangle, right? Or maybe, this didn't happen. Maybe instead, this was blue. But then I have a blue triangle. So blue triangle means that there is 3 mutual friends. Red triangle means that there are 3 mutual strangers. So one of them must be always there. So this is what this result says, right? If you have any 6 or more people, there will be either 3 mutual friends or 3 mutual strangers. Now this says something very fundamental. Okay, we'll discuss a little more about this later. But it says that this is something very much like the Pigeonhole principle, that if you are talking about very very large numbers, okay, 6 is not very very large, but compared to 3, yes, it is. Yeah, if you are talking about very very large numbers, then no matter how chaotic you try to make it, there will be still some order. Yeah, that is what this really boils down to. Okay, so what we are saying is that no matter how you are going to color with 2 colors for the time being, right, or some fixed number of colors, we will see later, you can still find very very structured subgraphs inside, smaller size but still with a lot of structure and properties that we are looking for. Okay. Now even stronger form of Pigeonhole principle. Suppose we have let us say uh, I think I made a mistake here. This is plus n1 plus n2 plus n3 plus etc plus nk minus k plus 1. Okay, so suppose n1 plus n2 plus n3 plus etc nk, so different numbers I'm just giving, minus k plus 1 balls are put into k boxes. So I have k boxes and I have some number of balls, right? This is n1 plus n2 plus etc plus nk minus k, right? From each I am subtracting 1 and then I am just putting 1 extra, right? So this is basically n1 minus 1 plus n2 minus 1 plus n3 minus 1 plus nk minus 1 plus 1. These many, whatever that number is, that many balls I am going to throw into each of the different boxes, k boxes. Then either the first box has n1 balls, or maybe that is not the case. Then the second has n2 balls, even that if that is not the case. Third box has n3 balls or something up to kth box has nk balls. One of these must be true. Now, all of them cannot be false altogether, right? Because if the first one had only n1 minus 1, second had only n2 minus 1, etc., last one had nk minus 1, in total we have only n1 plus n2 plus nk minus k. The plus 1 will be missing. So therefore, one of them must satisfy this. So now this gives more structure, right? We are saying that the first one now I can quantify and say that okay, this has n1 minus n1, or this has n2, or this has n3, or etc. I mean, I can change the order also. I can say that first one has n2, second has n1, doesn't matter. But this is something we can do. And we can use it to prove more interesting results. So here is a very simple example. So we have a drawer in the house, right? And then this drawer contains socks of different colors. Every day I go out, I want to, let's say, put a matching color for my my dress, right? The socks must have the matching color, maybe, I don't know. So now let us say that I have 5 red socks, 7 blue socks, and 4 gray socks. Now, one day you go to pick up the socks for the next day morning. You want to make it all ready, and then there is no power or something, and then you are picking up the socks from the drawers in the dark, so you can't see the color. So the question is that how many socks you need to pick to make sure that you have at least 2 of the same color, because I don't want to put a red socks on one leg and the blue socks on the other one, right? So therefore, how many you need to pick to make sure that you have at least 2 of the same color. So this is a problem, very well suited for the generalized version that we are just presenting, the strong form. So you have n1, n2, etc., nk minus k plus 1, right? So what are these numbers that we need to figure out, right? What are the balls? Now we know that the soxes are going to be the pigeon, and the colors are going to be the pigeonholes, right? Because we need to pick 2 of the same color. So therefore, we can already see that 2 of the same color must fall into one box, right? So that must be the blue box or red box or gray box. So now, what are these numbers that we want to talk about? So we have a red box, we have a blue box, and a gray box. So we have k is equal to 3. Okay. Then we have n1, n2, and n3, which says that we need at least, you need to guarantee there will be either n1 or n2 or n3, right? We need either 2 of the same color, 2 of the same color, 2 of the same color, 2 red or 2 blue or 2 gray, one of them, right? So n1 is equal to n2 is equal to n3 is equal to 2, and therefore by applying the generalized form, the minimum number of socks you need to pick will be n1 plus n2 plus n3 minus k plus 1, right? The same thing that we just saw. So what is this? This is n1 plus n2 plus n3, which is 2 into 3, 6, minus k, which is 3, plus 1, which is equal to 4. So if you pick 4 socks, then definitely one of them, one of the colors, there will be 2 of them, right? So there will be either 2 red, if it is not there, there will be 2 blue, that also is not there, there will be 2 gray. So that's it. So we are now masters of Pigeonhole Principle, right? Now we want to see some really amazing applications of this theorem. We are going to prove a very famous result called Dirichlet theorem. You know, Dirichlet is the name of a mathematician who proved this for the first time, at least. That's what people believe. And this is a result from analysis. You can say if you want that says the following, right? You are already familiar with numbers, right? You have integers, you have rational numbers, right? Can be written of the form p by q, where q not equal to 0 is an integer, right? And then you have real numbers, right? The real numbers are the extension of rational numbers, and you have also numbers which are not rational, right? Called irrational. So irrational numbers doesn't have a p by q form, right? There is no rational form. But what Dirichlet theorem says is that every real number has a very good rational approximation. That is, given any real number and given any epsilon, right? Any very small number that you give me, right? Like 0.0000000 100 zeros and 1 or something, I can find a rational number which is close to this number. The difference between them will be less than the number that you give me. So no matter what epsilon you give me, I can always find a number even closer. So this is the called Dirichlet theorem, right? This is that's a very good rational approximation, as good as you want. You can make it as small as the difference can be as small as you want. So let us state it in a formal way. So you have a real number x is given and a natural number n, positive natural number n is given. Then you can find two numbers p and q where q not equal to 0, such that the difference, the absolute value of x minus p by q, right? P by q is a rational number, is less than 1 by n times q, less than or equal to 1 by q square. So 1 by nq means that n can be arbitrarily large, which means that 1 by nq will be arbitrarily small. You can make it going to 0, like as close to 0 as you want. So the difference can be as close to 0 as you want. That's what it says. Now, how do you prove something like this using Pigeonhole principle, right? That is an interesting question. So can you prove this? I want you to think about this. So stop and think about it before you proceed. So here is the idea, okay? That no, when we are talking about real numbers, see, real number always have some integer part, which is not interesting really, right? Because that integer part is there. Maybe it is the larger part, but the fractional part is what is making it interesting. And we will start by assuming that since the rational number doesn't need a rational approximation, because that number is itself a rational number, so therefore the difference between the best approximation, which is itself, and that is going to be 0. So there is this part is trivial, right? Because this is difference is 0, so therefore we can assume that the number is irrational. So for the irrational number, the interesting part is the fractional part. So let us look at the number x given and then look at the fractional part. So fractional part of x I denote in the flower brackets. So this says that I remove the integer part from this, right? So this is equal to x minus integer part of x. So I take the fractional part. Now the fractional part is something we know about fractional part is that it is going to be less than 1 and it is going to be between 0 and 1. Right? We are talking about positive for the time. Otherwise we can just change the sign. It's not a big deal. So we have a we have a property that it is going to be between 0 and 1. Now this inequality gives us a clue. Okay, this inequality, maybe I shouldn't use this. So this 1 by n cube. So 1 by n is something that we can understand, right? Because you give me n, 1 by n is a very, very small number, epsilon. Now if I want to show that, the difference is going to be less than 1 by n, then basically what I am saying is that these two numbers happen to be in an interval of size less than 1 by n, right? So this is what we are basically saying, right? In this interval, we have uh, we have these two numbers, right? The number that we are talking about and it's this thing, they must be as close, right? So the difference is going to be very small. Now, how do you go about showing this, something like this? So since we already have a fractional part, and I know that it is going to be between 0 and 1, I'm going to subdivide this interval 0 1 into n sub intervals like 0 to 1 by n, 1 by n to 2 by n, etc., n minus 1 by n to n, I mean n by n, which is 1, right? So now I want to somehow bring the settings so that two things are going to fall in the same interval. Now what are these two things? So I need to somehow generate enough things to say that if I want to apply Pigeonhole principle, I need to generate at least n plus 1 numbers to be able to put it into, say that two of them are in the same interval, right? I'm going to have n intervals as my pigeonholes, then n plus 1 numbers must be there. So what are these n plus 1 numbers? So that gives the second clue. So for that, we are going to generate the numbers by using the fact that irrational numbers, even if you multiply with an integer, it is still going to be irrational. So what I am going to do is that I am going to take, our irrational numbers x and then multiply it with numbers, let's say 1 into x, then 2 into x, then 3 into x, etc., n plus 1. Oh, it's a problem with this, etc., n plus 1 into x. Yeah, maybe I need to use the other bracket. So I'm going to, yes, so n plus 1 into x with the other bracket, right? So I have generated now n plus 1 rational numbers. I am looking at the fractional part of each of these. So I get n plus 1 different fractional numbers. These are all related to x also, right? So we get a relation, and the interesting part is that if you look at the coefficients of what you have multiplied with, they are in the range 1 to n plus 1, so that the difference is going to be at most n. And that is what this 1 by n cube, and where our q is going to be in fact between 1 less than or equal to q less than or equal to n. Okay, this is an extra condition that you can give if you want. Okay. B. So that gives that's a clue to what is going to be our q, etc. So what we know is that by Pigeonhole principle, two of these guys, some ax and bx, right? Some ax and some bx, the fractional part must be belonging to the same interval, whatever some interval. Okay. So we know that fractional part of ax and fractional part of bx belong to the same interval. So that says that a minus b into x minus the integer part of a minus b into x, right? That is the fractional part, right? That difference, right? This is in the same interval, which means that this is the difference between these two, a minus b into x and integer part of a minus b into x. That difference is uh, less than a is okay is less than 1 by n because they belong to the same interval. Now, why it's strictly less? Because these numbers can never be in the boundary because they are irrational numbers, and 1 by n, 2 by n, etc. are rational numbers. So the fractional part will never be on the boundary, so it will be strictly inside. So if it is in one interval like this, then we know that they are going to be strictly inside, so the difference is strictly less than 1 by n. Now things are easy. So I am going to put a minus b as q. So q into x, because a minus b is going to be between 1 and n now, because the numbers are from 1 to n plus 1. Right? So a minus b is equal to q, and this integer part of a minus b into x, whatever it is to be p. Okay, it's integer part, so that's an integer. So qx minus p, right, less than 1 by n. So dividing throughout by q, because q is non-zero, right? I have taken distinct numbers a and b. The difference is going to be non-zero, and it is going to be in the range 1 to n. So therefore, this is dividing throughout by q. I get absolute value of x minus p over q is less than 1 by n cube. But now, because q is in the range 1 to n, this is less than or equal to 1 by q square. And that's what we wanted to prove. So we have proved the Dirichlet theorem by applying Pigeonhole principle, by considering the intervals 0, 1 by n, etc. as the pigeonholes, and the numbers that we generated, right, by multiplying this and taking the fractional part as the pigeons. And this is what requires some ingenuity. This is what we that makes the pigeonhole principle difficult to apply, because we need to figure out which are the pigeons and which are the pigeonholes, and that is not always the easy job. Okay, so I hope that you have cleared up the question. If there is anything, just think about it and let me know. Now, another very important result and very interesting application of the pigeonhole principle. This is Erdos-Szekeres theorem. Okay, so this theorem, I mean, we can prove it using the generalized form or the strong form, but I want to use the other form for the time being because it gives a different flavor to it. Right? It gives a different way in approach. It's a very beautiful approach. So the Erdos-Szekeres theorem says the following. Suppose you are given n numbers in a sequence. Okay, so like you have a1, a2, a3, etc. in some order. Now this n happens to be a number which is greater than or equal to r into s plus 1 for some positive integers r and s. Okay, so r and s are numbers. So r into s plus 1 is some number, and n is at least r into s plus 1, maybe larger. Now, no matter what the numbers that you have given me, right? So these are distinct numbers. No matter what order that you have given me these numbers, you can show that the sequence contains either an increasing subsequence of r plus 1 terms or a decreasing subsequence of s plus 1 terms. Now, what is an increasing subsequence? You take the sequence as it is and just remove some of the elements from there. What remains is a subsequence. And if this subsequence, every number right in the sequence, in the order whenever you go to the right, it increases. That is an increasing subsequence. A decreasing subsequence is exactly you take a subsequence, but it decreases each time. Now, what the Erdos-Szekeres theorem says is that you can find either an increasing subsequence of at least s plus at least r plus 1 numbers, or a decreasing subsequence of s plus 1 numbers. This is something that you can always do. Now, how do you go about proving something like this? See, in the earlier one, suppose we want to use the first form that we studied, right, rather than uh, the general form. Here we have several things that you want to show, right? You want to show either r plus 1 or s plus 1, right? General form allows this, but let's try to use the other form. Can you use the previous form to do this? That requires some thinking. So why don't you pause and think about it? Okay. Now, so to do this, I'm going to look at the sequence and then do some analysis. Okay. So A1 to AN is given. What I am going to do, because whatever you are going to give me, I have the collection, right? A1 to AN. Now I am the one who want you give me the sequence. I am going to show you that I can produce either a decreasing subsequence or an increasing subsequence of this many times. Right? So you have given me this thing. I am going to look at the sequence and study it. Now what I am going to do is that I count the number of or the length of the longest increasing subsequence that starts from a number. Okay, suppose if I look at the position, let us say A2, right? Now if I look at A2, I start from A2 and look at what is the maximum, the subsequence that you can create, which increases. So from A2, after A2, I can only select numbers which are larger than A2, right? Then I can select only numbers larger than that, etc. Right? So I look at this and see how many I can select. This I can do, right? Whatever. I'm just going to make an argument, right? So I'm going to say that whatever is that number, that I will call as xi. So xi is the length of the longest increasing subsequence starting at ai, right? So from a2 this is x2, from a3 it is x3, etc. an it is xn, right? From a1 it is x1. So I have this xi. Then I also look at the longest decreasing subsequence that ends at ai. That is the clever part. Okay. So look at the decreasing subsequence, but not starting from A2, but that ends at A2, right? Not starting at AN, but ending at AN. So what is the longest decreasing subsequence ending at AI? So this is YA. Now what is the property of or the advantage of selecting something like this is that if I look at the number that we are deciding now, right? For corresponding to AI, I have this numbers xi and yi. Now suppose I select any other number, let's say aj, j different from I, right? I have xj and yj. If I look at xi and xj, maybe xi and xj are the same, right? That is possible, right? Because xi is the length of the increasing subsequence starting from xi, and ai, and xj is the one starting from aj. Maybe from whatever is the longest sequence starting from ai is the same as the one starting from aj. That is possible, right? So xi can be equal to xj. Similarly, yi can be equal to yj, right? That is also possible, right? For any number, the decreasing subsequence ending at ai and aj could be the same, because after that everything is larger, then I cannot do anything, right? Whatever I have selection from ai, that is it. Next one is all smaller, larger, so I cannot select anything. So therefore it can be the same. But what I know is that xiyi and xjyj as ordered pair can never be the same. Why is that? See, if I select xi comma yi, that says that xi is the length of the largest increasing subsequence starting from ai, and yi is the length of the decreasing subsequence that ends at yi. Now when I go to aj, what happens? Suppose xi does not increase, then yj will increase because the numbers are distinct. If xi does not increase, then yj means, so if xi does not increase, that means that the number is going to be smaller. So therefore yj will increase. Otherwise, if xi increases, then yj, I mean, like if yj doesn't change, then the xi will change, right? One of them will change. Now, because of this, as ordered pairs, they will never be the same, right? I mean, this number and this ordered pair and this ordered pair will never be equal as ordered pairs. So this is never equal. So this helps us to design a pigeonhole application. So what you do is that we know that these numbers xi and yj can never be more than n, because maximum number of times is n, right? So longest increasing subsequence can only be at most n. Decreasing also can be at most n. So I'm going to plot it in a graph, like I take an n by n square. Then I'm going to put the numbers here, right? xi, so this is the position it's going to the I. So that is like 1 2 etc up to n, and 1 2 etc up to n. So this says that this is the where I am going to plot xi's, and this is where I am going to plot yj's, right? So how I am going to do that? Well, I take xi yj for any number, and whatever is the number I am going to mark it, right? So this guy, this guy, this guy, whatever I am going to. So the corresponding numbers I am going to put here, right? The ordered pairs xi yj I am going to put. If that pair is appearing, I am going to put a cross mark wherever it is. Now what I know is that because n is greater than or equal to r into s plus 1, okay, let me look at the rectangle of size s and r. Okay, if I am going to look at the s into r sub rectangle here, this rectangle will contain n boxes, right? This rectangle will contain n boxes because that is s into r boxes are there. Will contain s into r boxes, right? It can contain only not n boxes. It can contain at most s into r boxes. But n is greater than s into r, right? It's at least s into r plus 1. So therefore, even if you fill up all these boxes with cross, you will still have some uh, cross that must appear outside this box. It can appear either here, or maybe here, or maybe here, wherever, right? Now, if the the cross appearing here means that for some pair xi yj, right? Uh, you know the xi had crossed r, right? Which means that the longest increasing subsequence is greater than r plus 1, greater than or equal to r plus 1. If it was here, yj had crossed s, so therefore the longest decreasing subsequence is at least s plus 1. And similarly, if it is here, both might have happened, right? The longest decreasing subsequence as well as increasing subsequence is larger than r plus 1 and s plus 1. So these are the possibilities, and using the pigeonhole principle, right? The boxes as the pigeonholes and the crosses as the pigeons, the ordered pairs as the pigeons, we can show that Erdos-Szekeres theorem holds. And this is a very, very, very beautiful and very ingenious application of the pigeonhole principle, right? Okay, now time for homework. I will give you some questions. As I mentioned earlier, you need to look at more questions from the textbook. I would recommend to go through all the questions and try to solve as many as you can. But at least try to do half of them, something like that. So here are the homework questions. First question is let S be any n plus 1 element subset of the set 1 to 2n. Okay. So you have an n plus 1 element subset of 1 to 2n. So there is a 2n element set, exact precise set 1 to 2n. Show that there are two numbers a and b in S such that a divides b. This is a very classic result of Erdos. I want you to think about proving this rather than trying to look it online. You will find it very easily online, but don't bother with that, right? Try to try to find out a solution yourself. And it's fun. Okay, believe me, it is going to be challenging, but it will be fun. Now, so this says that any n plus 1 element subset of the set will contain two elements such that one divides the other. But what is even stronger one can show is that if you take some n element subset, that need not be the case. So give me an example of an n element subset of 1 to 2n where you cannot find two numbers with this property, right? So that is the first question. Then show that given any positive integer n, there is some integer k such that the digits of k times n. Okay, so it's a multiple of n, right? Are a sequence of ones and zeros. We are not talking about binary representation, because any number can be written sequence of ones and zeros, but not that. In the decimal system itself, I can find a multiple, right? Let us say that you take 37, you know that 111 is a multiple of 37, right? So this way, but maybe like 100, 117, 111 and 0, right? If you want both ones and zeros, you can add zeros, of course, right? So I want you to show that there is always a multiple. No matter what number you give me, you can always find a multiple with all the digits are just ones and zeros. Another question that is given a sequence a1 to an of positive integers, show that for some I and j between 1 and n, 1 less than or equal to I less than or equal to j less than or equal to n, ai plus 1 etc. aj is divisible by n. So there is a subsequence of consecutive terms whose sum is divisible by n. Okay, so that is the third question. And the fourth question is that show that if n plus 1 integers are chosen from the set 1 to 3n, okay, so I use this square bracket notation to denote the elements from 1 to that number, right? Whatever, if k is a positive integer, this says that we are talking about the set 1, 2, 3, etc. up to k. Okay, so when I say this basically 1 to 3n, 1, 2, 3, etc. 3n. So if you look at n plus 1 integers from 1 to 3n, then there are always two which differ by at most 2. Okay. And the next question is that given any set of 52 integers, there exist two of them whose sum or whose difference is divisible by 100. Okay. So now it's slightly different, right? Either the sum or the difference is divisible by 100. So can you show this? It needs little more thinking than the previous one. It's not very difficult. And sixth question, given 10 persons whose age is a whole number between 1 and 60, prove that one can find two groups of people disjoint having the sum of their ages equal. Okay, can we replace 10 with a smaller number? Yes or no, and justify whatever you say. Right? If it is yes, you need to give justification. If it is no, you have to give justification. Okay. Now